This is the last need-to-know topic I was saying for the course. Like any time I teach this course, I would feel like I would want to cover, of course, all the stuff we did, and then coordinate descent, ADMM, and Frank Wolfe. And then typically I rotate through other topics after this. So I think this is a very important method. I put it up there just maybe right below ADMM and coordinate descent, in the sense that personally, at least in my own experiences optimizing in the wild, let's say, I don't tend to use Frank Wolfe as much, but it's for reasons that hopefully will be clear, it's become popular because it provides you with something a little different from what you've seen already. So I'll just remind you quickly about ADMM we learned last time. We have problems of this form. The criterion splits up as f of x plus g of z, and the constraint is ax plus bz equals c. And if we don't have problems in this form, then we often will introduce auxiliary parameters or just new variables in order to get into this form, which we did for a lot of the problems that we discussed last time. And we form something called the augmented Lagrangian, which is, it's like, okay, in this form it doesn't look as much like the Lagrangian, but that's because we've defined a scaled variable. If you were to expand this out, we get a term that looks like W transpose AX minus B. Okay, this was just a typo. I'm sorry. This should say, of course, AX plus B minus C. It's just, that's the residual from the constraint. I had a typo in the slide there, plus W. If you were to expand this out, you get a term that looks like W transpose AX plus BZ minus C. That's the typical term in the Lagrangian. And then you get, for the squared term, just this guy, AX plus BZ minus C norm squared. That's the augmented part. And ADMM repeats the following steps. Stands for the alternating direction method of multipliers. We minimize over x, plug in for the most recent value, minimize over z, and then do a dual gradient ascent step. That's what this is doing. And it converges like a first order method. That's kind of what we learned. And it's a very flexible framework, so you can take a lot of problems and put them in this form. We saw examples of things you already knew how to solve, like lasso and other things of that nature. We also saw things that were SDPs that would have been much harder to solve with an interior point method, but that we could put in this form and solve with ADMM. So it's very popular because of the fact that it applies very broadly. And I guess I didn't put anything here about the distributed, but another nice feature of ADMM, which we went through last time, was that for certain problems, you can put them in ADMM form in a particular way that leads to an algorithm called consensus ADMM. So you can define multiple copies of your variables, set them equal to one common copy, which you might call the consensus variable, and then typically, let's say, one of these updates, like the x update, will decompose then. And you can perform parallelization with ADMM in that way. Another kind of very important feature of ADMM. Okay. So the motivation for Frank Wolfe, which we're talking about today, is projected gradient descent. So let's go back to one of the first things we learned, which was, well, we learned gradient descent, then we learned proximal gradient descent, and we saw that a special case of proximal gradient was projected gradient. It's this method. And this is the method. I take a gradient descent step on my criterion F for a constrained problem of this form. And then after every iteration, I project onto the constraint set C. Right? So you can imagine, like, I have some constraint set, and I take a gradient step, maybe it puts me here, and then I project onto the constraint set. That's my next iterate. Okay, so this would be xk minus 1. This would be xk minus 1 minus tk grad f xk minus 1. But it's not feasible, so I project it back onto C. And at some point, I would arrive at the solution. We need to know what the projection operator is, of course, to do this method. Right? And as I mentioned, when we talked about projected gradient, that's kind of a case-by-case basis. Sometimes you know the projection operator, sometimes you don't. Sometimes it's cheap and sometimes it's expensive. Just depends on what your constraints are. And moving from kind of one form of constraints to another form of the constraints could actually drastically change the difficulty of your projection operator. So for example, if your constraint set is a polyhedron, okay, so if your constraint set is, for your problem, if C is the set of, let's say, x such that ax less than or equal to b, then in general this is very hard. So it's hard to project onto a constraint set of this form. That's pretty much a QP at that point, solving a QP. For a general A, B, this is hard. But for some polyhedra, the projection is very easy. So one example of this is the simplex. Okay, this is linear time. Okay, and I could give you other examples of polyhedra that have efficient projections, but some cones, some polyhedra you can project onto easily, some you can't. So we're going to learn a method today that is an alternative to projected gradient, essentially, which doesn't involve projections. So for that, we're going to remember how we got this update. Okay, this update was gotten by thinking of this gradient step, x minus t times grad f of x, as the minimizer of a quadratic expansion of our function around the current iterate. So let's suppose the variable in our quadratic expansion is called y. Then I can think about, let's say, expanding f around the point xk minus 1, and I would get f of x k minus 1 plus this stuff, but I'm going to throw out that first term because it doesn't depend on y. Right? And this is the linear term, the approximation. It's just the gradient times transpose y minus x, and this is the quadratic term, 1 over 2t, the norm of y minus x squared. So I think about this plus f of x k minus 1 as a quadratic approximation to my function at the point y. And if I were to minimize this quadratic approximation, I would get exactly this gradient update, x minus t grad f. That was, in fact, the motivation for gradient descent. And then we just project that onto our constraint set. Right? So we have our function. We make a quadratic approximation to our function around some point, right? Xk minus 1. That brings us to this point, which is the minimizer of the quadratic approximation. That is the gradient step of this form. So it's the same motivation as for gradient descent. We just always project onto the constraint set. So we're going to do two things differently today. The first is that we're not going to do a quadratic expansion. We're going to do something else. And we're not going to do projection. We're going to do something else. So we're going to change both this and this. That's going to give us a different method. That method is due to two people in the 50s, Frank and Wolfe. I think it's 1956, so it's called Frank-Wolfe. The Frank-Wolfe method. It's also called conditional gradient method, but I just don't like that name. To me, the word conditional does not make sense to me, maybe because I'm a statistician. So you'll see it written as conditional gradient method, but I think a lot of people call it Frank-Wolfe method. So it does something differently, which is that it actually uses a local linear expansion of f. Okay, so it doesn't use this term. It just uses the linear term. So let me ask you before we actually present the method, why can't I make a linear expansion and then project? What's wrong with that method? If I made a local linear expansion, so I didn't have this term, and then I found the minimizer and I projected, what's the problem with that? Yeah, in fact, it will be infinity unless somehow this is 0. In which case it would have been at the solution. So if we try to minimize a linear function, unless somehow let's say you're trying to minimize A transpose X, right? The minimizer is going to be off at infinity somewhere unless A is 0. Right? A is the all zeros vector. So we can't try to minimize a local linear expansion and then project, because just minimizing that is going to not make any sense. It'll give us something off to infinity. So instead of doing this, instead of projecting the argmin over all y of grad f of xk minus 1 transpose y minus xk minus 1, instead of this, which doesn't make sense, because the minimizer is going to occur off at infinity. So this doesn't make sense. What Frank and Wolfe thought to do, which I think is very clever, is just to minimize this linear function over the constraint set. So don't do it in two steps. Don't make a linear expansion, then project. Just minimize the linear expansion over the constraint set. So just take the argmin over all y in the constraint set C of this linear approximation to our function. Okay, and this thing is sometimes called the linear minimization oracle. So the rule that brings us, let's say, from x to y, so minimizing y, is sometimes called the linear minimization oracle. Think about it as something different than a projection, right? The projection is some other rule. This is a different rule. And the key to Frank Wolfe being usable is that is the observation that this is often known in closed form when projections are known in closed form, and even outside of cases when projections are known in closed form. So we're going to see lots of examples that verify that. Okay, so you might think we should just take xk equal to this. That would be a decent method. Right, I would take xk equal to this minimizer, but in fact that's not going to converge in general. So Frank and Wolfe were clever kind of in two ways. The first was to figure out that I could make a linear approximation and minimize it over my constraint set. The second was that I don't have to move fully in that direction. I can just move in some amount. So this is the method. So S here represents y minus x. So S represents this. It's the direction we're taking for our update. So we first define S. Okay, sorry. This is another typo on the slide. Someone didn't recognize that. We're going to say sk minus 1 is equal to the argmin over all points such that xk minus 1 plus s is in our constraint set. Okay, I'm sorry. I just keep confusing you. If S was the update direction, that would be true, but S stands for Y here. There's no reason why that's... I had looked at this in a second and thought that S had to stand for Y minus X, but this product, gradient of F transpose X, is a constant, so we can throw it out. And that's all I was doing here in this slide. So S stands for Y, and this is totally fine as written. Okay? And okay, so the point is that instead of just taking the next, this optimizer, which is the optimum of our linear approximation over our constraint set, I take a convex combination of the point I'm at and that new point S. So it's exactly as written in the slides. There's no typo up there. I just do this, and then my next thing is to take a convex combination of, the point I'm at and the point that I might move to. Okay. So there's no projection. The update is solved directly over the constraint set C, and there is actually a default choice for these weights in this convex combination, and that's 2 over k plus 1. And that choice is made in order to facilitate the proof. The proof is that this converges and has a certain rate is very simple with this. It's not the only choice. I'll come back to this a bit later. And how do we see that we are in the constraint set? See? Well, we can see that by convexity. That's it, of the constraint set. This is in the set C by construction. This is in the set C, let's say, by assumption, if I've been feasible up to now. And so this is a convex combination of 2 points in C, and provided C is convex, which we are assuming it is here, they're convex combinations in C. Okay, we can also rewrite the update in this form, which was a bit of the source of my confusion when I told you that there was a typo here. So if we write the update in this form, then S minus X represents the direction we're traveling in, that we're going to be making this move in. And this update is equivalent to saying, if we're going to start at X, we're going to move a little bit in the direction of S minus X. Gamma K times S minus X. So sometimes you'll see the updates written like this, and sometimes you'll see that I actually define this difference to be like V, for example, and then I could write a rule for V up here. So it's just an equivalent formulation, whether or not I'm solving for the update direction or for the linear minimization point itself, S. Okay, so in this form, we can see that we're moving kind of less and less in the direction of this linear minimization oracle as we proceed, right? Because these gamma k's are diminishing like 1 over k. So as the algorithm goes on, the linear optimization oracle is telling us move here, and we're just taking kind of a bit of progress towards that at each step. We're not making a full move. This gamma k is not 1. So here's a picture from this recent paper by Martin Yagi. So Martin Yagi is, he wrote a number of papers on Frank Wolfe, and I think it's in large part due to him that this is so popular today. It's another example, along with ADMM and coordinate descent, where it's an old method, lots of old literature, people in optimization forgot about it, and then it kind of got popular recently because people found that it was a very good method for lots of problems in today's landscape for statistics and machine learning. Which is, I think this is his thesis, or maybe a paper from his thesis, I can't remember which one. So this is the picture. I have some convex function f, and we're assuming here that it's differentiable, right, because I'm accessing its gradient when I talk about the linear approximation to it. I have some constraints set. Here he calls it D. That's maybe this set. And I make a linear approximation to my function at the point x. That's what this brown plane is. And that brings me to some point S. Right? The point that minimizes this linear approximation over my constraint set is this point S. And instead of moving from X to S, I just move a little bit in that direction. I move amount prescribed by these weights. Or I can also think about it like this. I take a convex combination of X and S, and that's where I go to. Okay, any questions at this point? So I'm going to just walk through a bunch of different examples and try to convince you that this is broadly applicable. And there's a kind of one set of examples that give you a prescribed rule for the update, and that's if you have norm constraints. So I'm just going to point out that in generality. What happens if your set is a norm ball? So if you have some norm, and the constraint set is a set of all x for which the norm of x is less than or equal to t. So this can be an LP norm, this could be a matrix norm, it could be any norm. Then by our rule for, by our knowledge of what the dual norm is, and our rule for subgradients of maxima, we can kind of generally characterize what these updates look like. So remember, by definition, S is in the, S minimizes, okay, the gradient transpose S subject to all points S that are in the set C, but that's, for us just now, the norm of S less than or equal to T. Okay, and what I want to convince you is that minimizing let's say, if I minimize this, it's the same thing as negative max of negative f of x transpose s. right? Those are the same thing. And because this is a norm, okay, if I define because this is a norm, this is equal to this. Okay, so this should say z, sorry. So if I look at all points that have norm less than or equal to 1 of minus the gradient transpose the point z, then I can rescale this, right? Because of the fact that this is a norm, this is just going to be equal to essentially 1 over t times what I got when I had the norm being less than or equal to t. And the last thing is I can call this gradient transpose minus z, right? And that'll be the same because the norm of minus z is the norm of z. So it doesn't matter whether I have negative gradient or gradient, because essentially this constraint set is symmetric around the origin. I can write it like this. Okay, so this is all just manipulations because I have a norm. So what that means is that if I look at the minimizer, of the gradient transpose S, this is equal to whatever I have written on the slide, minus t times argmax gradient of f of x transpose S. So sorry, I just got to scale up for you. The minimizer that we're looking for is equal to minus t times the maximizers of gradient of f transpose S. And what is this? Okay, this thing is actually exactly equal to the subdifferential of the dual norm evaluated at the gradient of f of x. Right? The dual norm, to remind you, is equal to the maximum over all points that have norm less than or equal to 1 of z transpose S. That's the definition of the dual norm. And if I ask you for subgradients of this, then by your rule for the subgradients of maxima, it's the maximizers here. If you're confused about that, then go back and look at the slide on the lecture on subgradients. So this comes from the rule for subgradients of max. So what we've learned is that the linear optimization oracle, the guy that we pass in a linear approximation, asks it to minimize that linear approximation over a constraint set, and it gives us the answer. It's no different for norms, for norm constraints, as knowing subgradients of the dual norm. So you need to know what the dual norm is, which in many cases we do. We know what the dual of the L1 norm is. We know what the dual of the trace norm is, etc. And we also know how to compute their subgradients. So that is what we need to know in order to apply this method for norm constraints. And we just take a subgradient and multiply by minus t. That is the update rule we're looking for. Okay, and a key, or one key which makes this effective in a lot of problems that we see in machine learning, is that this is often simpler or cheaper than projecting onto the norm ball. Okay, taking a subgradient of the dual norm is often simpler or cheaper than that projection. Questions at this point? Okay. So here's what we're going to do. We're going to go through a bunch of examples. I'm going to tell you about how this converges, and the answer is it converges just like projected gradient. So it's really, in fact, the analysis and everything is very similar. Or maybe the analysis isn't all that similar, but the the results, the constants you get, the assumptions, everything are very similar. And I'll talk about some variants of Frank-Wolfe and a very important property it has, which projected gradient doesn't have. And then I'll talk, if we have time, about this idea called path following. I'm not sure we'll get to this, but I think it's a neat extension that we'll talk about. So let's talk about an alternative to doing projected gradient when your constraint set is the L1 ball. Right? So if we were to solve something like the constrained form of the lasso or the constrained form of the logistic lasso or any constrained form of L1 regularization, we'd have some function subject to the L1 norm of our parameter being less than or equal to t as our constraint. And we could do projected gradient, but let's ask what would Frank-Wolfe do and kind of compare them. So Frank-Wolfe, because of this rule here, I need to know what the dual norm of the L1 norm is. I need to know what its subgradients are. And if I know that, I can apply the method. So the dual of the L1 norm is the L infinity norm. That should hopefully be familiar to you at this point. Right? In general, the dual of an LP norm is the LQ norm. So if I take the dual of the LP norm, maybe I should write star down here. I get the LQ norm, where 1 over p plus 1 over q is 1. And so if I take p equals 1, then I need to take q equals infinity in order to satisfy this relationship. And what are the subgradients of the max in absolute value? That function, max of all the coordinates, well, you know what that is. I simply, a valid subgradient, for example, is to take one of the components that achieves the max in absolute value and put all of my weight there. Right? So if the ith component achieves the gradient, then a subgradient is EI, the standard basis vector with a 1 in the ith component and zeros everywhere else. So Frank-Wolfe repeats the following updates. Man, this is really annoying. Sorry, this keeps going blue on me. Frank-Wolfe repeats the following updates. It finds the maximum and absolute value of the gradient component-wise. So it looks at the ith component of the gradient for all I, takes the biggest one in absolute value, and then it multiplies the subgradient, which is this thing, by minus t, and takes a step size of gamma k. So what does this look like? This kind of looks like to us like greedy coordinate descent, right? Because coordinate descent would repeatedly take an update in the direction of the negative gradient cyclically. Like I would go from the first component to the second component to the third component, etc., or maybe some permuted order. This thing chooses to make the update in the direction of the component that's largest. It's going to make the largest progress. So it's like a greedy coordinate descent. And the difference is that here I have diminishing steps. That's not required for Frank-Wolfe. That's just the method I've taught you so far. Okay, so instead of taking some large step, you can think about it, I'm just moving a little bit in this direction. But this is the update, which is extremely cheap, right? I just scan the components of the gradient and I move in the largest direction. So it's trivially order n, right? Because I have to just make a pass over all the components of the gradient in order to do this. So it's a lot simpler than projection onto the L1 ball. So projecting onto the L1 ball, it turns out, is also doable in order n steps. So they're actually, it's not only cheaper, but this is a pretty sophisticated algorithm to get you this. It relates to projecting onto the simplex. So you can reduce a projection onto this L1 ball to a projection onto the simplex, and then there's an algorithm that is a bit clever that gets you a linear time projection. Okay. So let's talk about LP regularization now. So more general, let's suppose that this is your constraint. It's the LP norm less than or equal to t. So the dual norm, as I mentioned here on the notebook, is the LQ norm, where p and q are complementary pairs. They satisfy this. 1 over p plus 1 over q is 1. And what are the subgradients of this? So I think on previous years I put this on a homework, but I'm just going to tell you what it is now. This is the subgradient. So it's actually, you can compute subgradients of any LQ norm efficiently via this rule. So the subgradient is, in fact, sorry, this is minus t times a subgradient. So I'm telling you what this whole thing is going to look like. Okay, but if you ignore, if you ignore the minus sign and this scaling alpha, this is like what a subgradient looks like up to scalar factors. So in the ith component, I take the sign of the gradient in the ith component times the absolute value of the gradient times p over q to the power of p over q. You can check that this achieves the max in the problem that defines the LQ norm. And you can check that indeed the norm of this thing is in the q norm is equal to t. So once I remove the scaling, the norm is equal to 1, which is what you need. So once I know this, I just do the Frank-Wolfe updates as usual, right? I just add gamma k times this to 1 minus gamma k times xk minus 1. That's my update. So this is a lot simpler than projecting onto the LP ball for a general P. And in fact, aside from special cases, you won't know how to do that projection. So when P is 1, 2, or infinity, you can compute them. So I just told you what this one was. It's doable in order n time. This one is kind of trivially doable in order n time. This one's just truncation. And this 2 norm one you also know. It's just dividing by the 2 norm. So take a vector, I divide by its 2 norm, it puts it on the 2 norm unit ball. That's the projection operator as well. So those cases you know, but aside from that, it's not, at least I'm not aware of work that does this in general. And this is a very simple rule that you can use to make optimizations over the p norm constraint. Let's move on to a matrix valued problem. So this is an example now where you have a much cheaper linear optimization oracle versus projection. This is like a really big difference computationally. The trace norm ball. The trace norm ball of radius t. So and this is again a norm. So I need to know what the dual norm is. I need to know how to take subgradients of it. The dual norm is the operator norm, something I think you guys we've mentioned for sure and perhaps appeared in the homework. So this is the sum of the singular values. This is the largest singular value. Okay, so it's the same analogy between the L1 norm and the L infinity norm for vectors. This is like the L1 norm. This is like the L infinity norm. And the subgradients of this thing are of this form. So ignore the minus t. It's just UV transpose, where u and v are the leading left and right singular vectors of this matrix. Okay, the proof of this is actually somewhat simple. In class, I believe when I tried this, at least I kind of massacred it, so we had some difficulties. To take the subgradients of the trace norm are a bit more difficult, but still doable. And we tried that in class. To take the subgradients of the operator norm are much simpler. In fact, it's just this. So you can check, for example, directly this achieves the max. This is just using the definition of the operator norm, and that this has the desired trace norm. So all I need to do is to take, for example, run the power method. I run the power method on my matrix to get the leading left and right singular vectors, and then I'm done. I can make my update. Which, for example, if this is sparse, is very cheap, right? The power method reduces to multiplications of my matrix, and I can get these leading left and right singular vectors. How about projecting onto the trace norm ball? What's the alternative? Well, that requires an SVD. You learned that also. I mean, we kind of learned that when we talked about proximal gradient, but maybe you can just trust me that requires an SVD, like a full SVD, whereas this is just the top left and right singular vectors. Okay, so much simpler and much cheaper. So we've been talking about a bunch of problems in constrained form and how Frank Wolfe is cheaper or simpler or both than projected gradient for some of these cases. From an optimization point of view, that's kind of like the full story. That's definitive, and if you really cared about this problem, then this is a cheaper update. From an ML point of view, or from a statistics and machine learning point of view, we don't typically have a strong preference for constrained form versus penalized form. We just think about whatever form is more convenient, and then we solve the problem over a range of tuning parameter values. Right? If you cared about this problem, and most of the times in practice, you'd be solving this problem over a range of t's. And you'd be doing something like cross-validation at the end in order to determine which solution you like the most, or some other method. And what you would do in practice is you say, if this was hard, you'd rather just solve this over a range of lambdas. Okay? And then I would choose, again, the best solution via cross-validation or some other means. So maybe from a ML and stats point of view, we should really be comparing Frank Wolfe to either projected gradient or proximal gradient, where we use the proximal operator of this norm, depending on which one was easier. Now, even that is a subtlety, because I don't want to go on too much of a tangent, but statistically speaking, these are still not equivalent. So solving this problem for the best fixed t and solving this problem for the best fixed lambda, where best means something like it gives me the best error, those are different estimators. They actually don't have exactly the same operating characteristics. The equivalence that brings us from this problem to this problem is data dependent. So there's a particular mapping that takes us from t to lambda or from lambda to t, but that's a random mapping if we have random data. So if you think about somehow like statistically choosing the best, they're still not exactly the same. Okay, that's maybe a longer tangent. To first order though, if you just wanted to find an estimator that had some regularization corresponding to the norm, you would just choose whichever form is easiest and solve it over a range of parameters. This is really annoying. I'm sorry. I'm having to prop this up in order to get rid of the blue. Okay, so hopefully those ramblings made sense. It's fair, probably, to compare Frank Wolfe to either projected gradient or proximal gradient, whatever is easiest given a particular norm. So that's what I'm doing here. And the L1 norm, well, we already saw that projected gradient is, order n. Proximal gradient for the L1 norm is also order n. So in fact, either proximal gradient or projected gradient, they're as cheap as Frank Wolfe, and there would be no real reason to use Frank Wolfe over those methods, at least not the version of Frank Wolfe I described, for the reasons I described. For the LP norm, the proximal operator is just not generally computable. So I can't tell you what the LP norm is, the prox of the LP norm is for p equals 3. I don't know what that is. Whereas we can still compute Frank Wolfe. It was that simple thing I showed you. And for the trace norm, the proximal operator, as you learned when we talked about proximal gradient, is still requiring an SVD. Okay, so either projection or prox operation is expensive for the trace norm. It's much cheaper for Frank Wolfe. Okay, so I'm just trying to say it really is a fair comparison. Yeah.
What's the complexity of the power method and method for computing the Buckner singular values?
That's a difficult question to answer because it depends on the spectral gap. So it'll be linear convergence in the difference with a contraction factor that relates to the difference in the first and second eigenvalues. Excuse me. So if you have a big spectral gap, it'll converge very quickly. If you have no spectral gap, then it'll possibly not converge. But whatever it is, it's cheaper than SVD. So any method that you use to compute an SVD, you could also use to compute the largest left and right singular vectors and stop early. And the power method was just a simple, a particularly simple method for computing the top singular vectors. Any other questions? Okay, there's lots of others, by the way. There's a ton of other problems that Frank Wolfe can solve. So I would just say see Martin's thesis or some of the papers he's written. There's a lot of other ones. All right, so I'll just make a comparison to the lasso, and then to projected gradient for the lasso, and then we'll take a quick break and come back. So upshot is, like, look how broadly it applies, look how easy it is. And it has theoretically good convergence properties, just like projected gradient. And it has one other special property that I'll hold off telling you until a little later that is very different from a first order method, typically. Downside is that, at least in my experience, and this is why I haven't used it often in practice, it does not converge practically as quickly as first order methods. So everything I told you is true so far. Like, this is a very cheap update. Okay, I've tried this for matrix completion, and perhaps I'm not optimizing as the problem as best I can in terms of step sizes and whatnot, but at least in my attempts, it converges a bit slower than typical first order methods in terms of iteration complexity. So here's just an example of that with Frank Wolfe versus projected gradient for the L1 norm case. So both have order n iteration complexity, and this is the difference in conversions. So we notice two things. First, that it's not a descent method. Okay, the criterion's bouncing up and down. And second, it's converging slower than projected gradient. And this is pretty typical in my opinion. So when I've talked to people who are Frank Wolfe fanatics, and I've mentioned this, they've said, oh, step size optimization. You should use step size optimization. So I didn't here. I just used the fixed step sizes. It's certainly true it could help. I just haven't found it to make a huge difference. But, you know, let's just take these comparisons in mind, but I would do your own comparisons in practice. All right, let's take a quick break, and then I'll tell you about more of its properties. Okay, I'm going to jump back in because there's a bunch of things that I'm hoping to cover, and I'm being optimistic. Hopefully we get through them all. I'm going to continue telling you a bunch of good features of Frank Wolfe, which are not as easy or not possible for projected gradient. And I mean, again, the kind of caveat to keep in mind is that it can have a bit slower convergence in practice, but it has a bunch of other nice features. So one such nice feature is that you get a very natural duality gap out of Frank Wolfe. So in optimizing the linear approximation over the constraint set, so just in computing that point S in the Frank Wolfe updates, you get a duality gap. And this is the quantity right here. So if you take the gradient of your function at iteration k, transpose xk minus sk, okay, this is the point you were at the kth iteration. This is the point you're going to move to at the k plus first iteration. Okay, but you'll move a convex combination of the way between x and s here. Then this is an upper bound on how far you are from optimality. So I'm calling it a duality gap. I'm not telling you where the dual comes in yet, but I will tell you shortly. But it upper bounds f of xk minus f star. And the proof is extremely simple. Here's the proof. The first order condition for convexity tells us the following. Because f is convex and it's differentiable, if I were to make a linear approximation of f around the point xk, compare the criterion at S to the linear approximation at S, then the criterion has to be lower bounded by the linear approximation. Right? The picture of that is this. Any convex function is lower bounded by its tangent line everywhere, around any point. So that's a fact by convexity. In fact, it's equivalent to convexity if f is differentiable. And we can minimize both sides over S in the constraint set C. Right, this is valid for all S, so I can apply the minimum over all S to both sides to see what I get in the constraint set C. The left-hand side gives me f star. By definition, that is the minimum of f of S for over all S and C. And the right-hand side, well, the only thing that depends on S is this bit. So I'll just propagate the minimum operator into that piece, leave this untouched. And this minimum is achieved at the point sk by definition. Right? That's how we define sk. It minimizes this. So I'm just writing that here. It's equal to the inner product of f of xk with sk minus xk. And now I just have to rearrange to get this duality gap, right? Suppose I subtract f star to this side, and I move this term to the other side. I get f of x minus f of xk minus f of x star, right? This is what I have, f star bigger than or equal to f of x k plus gradient of f of xk transpose sk minus xk. I'm just going to rearrange this, right? Move this to this side. I'm just going to switch xk and sk. And move the f star to this side. I get f of xk minus f star, which is what we were claiming, right? This thing, which I have just anyways from doing Frank Wolfe. I always have this. I don't have to compute anything extra. Upper bounds how far I'm away from f star in criterion value. Okay. Why is this called a duality gap? Well, I can maybe just briefly walk you through why that's called a duality gap. Because somehow what's important is this relationship. It's not important where the name comes from. But it does come from, we can also think about it from the perspective of the dual. And so I'll tell you that kind of quickly. This is our original problem. It's f of x plus the indicator that x is in C. I'm just writing the constraint as an indicator. The dual, as hopefully you know from all the work you did on the homeworks and the lectures we did with duality and conjugates, we can express in terms of conjugates. And I can write the dual of this problem as maximizing minus f star of u minus I star, where this is the dual of the indicator function is the support function of the set C, evaluated at minus u. And the duality gap at a point x and u is the difference between the primal criterion and the dual criterion. Okay, but if I'm at a point x and u that are primal and dual feasible, this indicator is 0. So the difference in these criterions is f of x minus this, and the negatives cancel. It's f of x plus f star of u plus I star of minus u. And now I'm using Fench's inequality. Okay, that the sum of f star of x and f of x and f star of u is bigger than or equal to x transpose u. It's a fact about conjugates. We call that Fench's inequality. And if I were to evaluate, if I were to evaluate this thing at xk and this particular dual iterate, which is the gradient of f at xk, I get exactly this. So it's another way to see that it's a valid gap coming from the dual. This proof is obviously much simpler. It didn't invoke duality at all. This is just where the name comes from, an alternative argument through duality. Okay, any questions? Did you say the last slide? I didn't hear what you said. Last line. This. This is just evaluating this at the point x equals xk and u equals the gradient of f of xk. Okay, so x transpose u becomes this, and the support function, which is defined as the maximum over the set C of its argument transpose a point in the set C. Okay, but the argument is minus u, so it's minus the gradient. This is achieved by sk. So this becomes gradient of f of x transpose x plus or minus the gradient of f of x transpose s. So it's exactly this quantity you saw previously. Okay. So moving on, there's a very nice simple convergence analysis for this that's due to Martin Yagi. That it has essentially the identical form to what you saw for projected gradient, it just uses a different notion of curvature. So instead of the Lipschitz constant of the gradient, it uses something else. And this is what it uses. It actually looks kind of crazy to define, but I'm going to relate it to the Lipschitz constant of the gradient in a second. So there's a particular quantity that defines the curvature of f over the constraint set C, and that's this quantity. I look at the difference between f and its linear approximation. So this is f, that's its linear approximation. The difference is right here, f of y minus the linear approximation. And I look at how, the biggest I can make this. Times 2 over gamma squared over all points x and s in the constraint set C, and y that's a convex combination of x and s, where the weights are 1 minus gamma and gamma. Okay, so that's how we define the curvature constant. This is the very biggest I can make that. And for a linear function, there's no difference between the function and its linear approximation. So this is 0. M is equal to 0. Otherwise, this would be non-zero. It's going to be positive, and it's going to be big if f is highly curved over the set C. And just as a side note, next time, no, not next time, the time after next time, we're going to talk about mirror descent, and there's going to be an important measure of, it's not really a distance measure, but people kind of think of it that way, called Bregman divergence that we bring up then. This is the Bregman divergence. It's exactly this. It's the difference between f and its linear approximation. We call it the Bregman divergence between x and y defined by the function f. So I can think about this as measuring curvature with respect to this particular notion, this metric, Bregman divergence. Okay, so this is just some constant. Think about it that way for now. And the Frank-Wolfe method with the step sizes that were given to you, 2 over k plus 1, the suboptimality that it sees after k iterations is upper bounded by 2 times that constant m over k plus 2. So if we swapped out this m for L, where L was the Lipschitz quantity of constant of the gradient, this would be the exact same result you have for projected gradient. It would look like 2 times L over maybe k plus 1. Maybe that, actually can't remember, but I probably could be k plus 1. But in any ways, they both have a 1 over k rate or a 1 over epsilon rate if we think about the number of iterations needed to get to suboptimality less than or equal to epsilon. For now, they seem to be relying on different notions of curvatures. So the constants in this rate differ. Projected gradient uses the Lipschitz constant of the gradient. Frank-Wolfe uses this m. So let's compare this to projected gradient more carefully by asking how does m relate to the Lipschitz constant of the gradient L. So remember that if I were to, if I had a function that had a gradient as Lipschitz, then we used to write this like this. F of y is upper bounded by f of x plus grad f of x transpose y minus x plus L over 2 y minus x squared. You guys proved this on the first homework, in fact, that this was a consequence of grad f being Lipschitz. Okay, I can upper bound f by a quadratic around any point x, where this is the L defines the amount of curvature in that quadratic. So just subtracting off this bit to the left-hand side tells me that this Bregman divergence, the difference between f and its linear approximation, is upper bounded by L over 2 times y minus x squared. All right, that's just rearranging that inequality. So if I go to look at the definition of m, which maximizes this quantity over all x and y in the set, then I can upper bound this by this. And I can upper bound m, therefore, by the maximum of, so the definition of m is 2 over gamma squared times this Bregman divergence, but I'm going to upper bound that by L over 2 times y minus x squared. And now a short calculation tells you that, in fact, so the 2's cancel, and I get to get an L. This quantity, overall, y that's related to points x and s in the set in this way, it's a convex combination of points x and s. It turns out to just reduce to the maximum over all points x and s in the set of the distance between x and s squared, which is just L times the squared diameter of my set. So if I think about my set having some diameter, this is telling us that we can relate m to L in this way. M is upper bounded by L times the diameter of my set C squared. So if I had the Lipschitz constant being something, I immediately have this upper bound on m. So it's not really that much stronger to assume this curvature constant being controlled versus assuming that the Lipschitz constant, the gradient, is controlled. Okay, it's a very similar assumption. Right, in particular, we know that now we immediately see that if f has a gradient that's Lipschitz and the set C is compact, then it immediately has a curvature constant that's finite, and that's at most L times the squared diameter. I might skip this because I wanted to get to other things. The proof for Frank-Wolfe converging at that rate, 2m over k plus 2, that upper bound, is not difficult, and it's all in the slides. So the entire proof is contained in these 2 slides. And I don't necessarily think it's insightful. It's just a matter of manipulating essentially the duality gap. So it uses this. It uses this duality gap. So this is not only kind of a practical thing to know when it's taught the algorithm, it's also helpful for the proof. So I think I might skip this, and I'm happy to do it if we have time at the end, but I want to tell you more about Frank-Wolfe. Okay. So let's just for now skip that. You have a question?
Slightly confused why gamma equals to 1 should be in the k max there.
Oh, it doesn't attain the max. So yeah, I think it's maybe the subscripts are too small in the max. So this is the max over all points x, s in the set C, gamma that's between 0 and 1, and y that's equal to 1 minus gamma x plus gamma s. And this, what we have is something like this. Actually, there's no 2 anymore. It's just 1 over gamma squared times the norm of y minus x squared. Okay, and so we should be able to do a quick calculation, plug in, let's say, this is equal to the max. I'm just going to plug in for y here over all x and s in the set C, and gamma in between 0 and 1 of 1 over gamma squared times 1 minus gamma times x plus gamma s minus x, norm squared. And what we should see is that this is equal to this. Okay, this is equal to gamma x minus gamma s, or gamma s minus gamma x. So if I pull the gamma out, it cancels with this square. This is just equal to then maximum over all x and s and x in the set C of x minus s squared. So it didn't end up mattering somehow what gamma was. It didn't appear in the max anymore. Any other questions? Okay, so like I said, we'll skip this for now. So let me tell you about some other properties. Actually, really one other important property. Then about some variance, and if we have time, I'll talk about path following. So one important property of Frank-Wolfe that is not shared by projected gradient, and that you've only seen surface in second-order methods, is affine invariance. So I think it's a very intriguing property of Frank-Wolfe, because it's not using second-order information. It's only using the gradient. But the way that it's set up is such that the updates are actually invariant to affine transformations. And that's, it really comes from the fact that we're minimizing a linear approximation. So let's suppose that I change my coordinates, and I define, let's say, x to be a times x prime, and f of x prime to be f of ax prime. So this used to be f of x, now it's f of ax prime. And I'm going to consider running Frank-Wolfe on this function f, which operates right in a different space, x prime, versus what I would have done if I ran Frank-Wolfe on little f, which operated on x. And Frank-Wolfe on x prime repeats these steps. So this is exactly as you know it. It's just a gradient transpose like z. And I find the s that makes that the smallest, or I'm calling it s prime. And then I move in the direction of, or I take a convex combination of x prime and s prime, where the weight is gamma, to get to my next iterate, calling this x prime plus. So what's the difference? A difference is that actually the constraint set has become A inverse times C. So we're assuming that A is invertible. Right? If I had x being in C, and x was equal to A times x prime, that's the variable transformation that we're looking at. That's the same thing as saying that x prime is in A inverse C. This just means multiply A inverse by all the elements of C. Okay, so that's why that's the constraint set here, because this is my constraint set in the transform space. So it turns out that this is in fact exactly the same as Frank-Wolfe on little f. Why? I can just think about multiplying by A, and I'll see that I get the same. Right. So if I multiply by A, in the update equation here, if I multiply both sides by A, then I get this. Right? And this thing we're calling x. So if this thing were equal to s, if this equals s, which was the Frank-Wolfe update on little f, then we would get back the usual Frank-Wolfe update. On f. Right, so now we need to check that somehow the Frank-Wolfe update s prime on capital F, after I multiply by A, gives me the same Frank-Wolfe update I would have gotten on f, little f. So A times s prime is A times the minimizer, should be no prime, A times the minimizer overall z in A inverse C of the gradient of f of x prime transpose z. So this is A times the minimizer overall z in the set A inverse C. So remember, f of x prime was f of ax prime. So if I take its gradient, this is A transpose the gradient of f at ax prime. So I can write this as the gradient of f at the point ax prime transpose az. And okay, so now if I have Z in the set A inverse C. I can also write that as AZ being in the set C. And I can just call this AZ another variable. Call it W or something like that. A times the argmin over all W in the set C of grad of F of, and remember A prime X is just, A X prime is just X. Okay, so that's what the update looks like. And this should have just been the Frank-Wolfe update. So now somehow I have A times the update. Yeah, but I wanted to get that this was the Frank-Wolfe update, A times S prime. Oh, sorry. Of course. Going from here to here. Okay. This is the difference between mins and argmins. This is why this is difficult. The minimums match if I relabel AZ equal W, but the minimizers don't. The minimizer here is going to be A inverse what it was here. So by going to the argmins, I have to pull out an A inverse. Okay, just convince yourself that the minimums match if I relabel this, but the minimizing W is going to be A inverse times the minimizing Z. So I really should have said it's the argmin over all Z, left it as A inverse C. So that I'm looking for the minimizing Z. And that if I reparameterize by taking W equal to AZ, the minimizing thing here I have to multiply by A inverse to get what I had before. So that's what cancels with the leading A. Argmins are tricky. They're trickier than mins. So there you go. That's affine invariance. So this is the Frank-Wolfe update that I wouldn't gotten on F. So now I have 1 minus gamma x plus gamma times the Frank-Wolfe update. So like I said, I think it's like an intriguing feature of Frank-Wolfe. When I saw this the first time, I was really surprised because I've never seen affine invariance be preserved by methods other than methods that use second-order information. Somehow this does, which in principle is a very good thing for Frank-Wolfe because all these matters about like bad conditioning and somehow like doing things to improve conditioning and stuff, it should not be so affected by it. Even the analysis, by the way, is affine invariant. The curvature constant, which is not true of the Lipschitz constant of the gradient, the curvature constant is invariant to affine transformations. So that calculation I won't go through. It's fairly similar. You just use the chain rule here and then work out that the max doesn't change. It doesn't depend on a reparameterization of the function. So even the analysis is affine invariant, which, remember, for Newton's method required us to go to self-concordance, which was like this very difficult but elegant notion that helped us get affine invariance of the convergence analysis for Newton. For Frank-Wolfe, it's like the method is affine invariant and the analysis is affine invariant. It's just very simple. Okay, so in the few minutes I have left, I want to tell you about some of the variants, and then I guess I won't have time for path following. But some variants. We haven't seen this yet for projected gradient or proximal gradient. It exists. I just haven't showed it to you. If you don't optimize the linear optimization orbital perfectly, but you optimize it up to some error, you can still get similar convergence rates. And for projected gradient or proximal gradient, we have similar results. It says if you don't compute the proximal operator exactly, or the projection exactly, but you have some error, then that you can still get convergence as long as the error decays kind of sufficiently fast. And that's what's happening here. So instead of kind of achieving the exact min here, I'm saying suppose I take a point sk minus 1 that is bounded by the min plus something. And that something is m over 2 times gamma k times delta. M is the curvature constant. Delta is some error. This is like some parameter you can think that controls the size of the error. And gamma k is the step sizes. And notice that the optimization error we encounter, so even for a constant delta, the optimization error that we encounter on top of this is going to 0 at the rate 1 over k. So this is saying like you encounter smaller and smaller errors in your inexact updates. So if this is the case, then the convergence rate just becomes, the convergence bound just becomes what it was before, times 1 plus delta. So it doesn't change much. The same thing is true of proximal gradient and projected gradient. But in all these cases, we require the approximation error for the thing we're looking at, like here it's the linear minimization oracle, to go to 0. Right? And here it's going to 0 at the rate 1 over k. And the proof is actually not that much more sophisticated than what we have in the slides for Frank Wolfe. And lastly, I'll tell you about two variants of Frank Wolfe. One is kind of an obvious variant, which is just doing line search. So we could use backtracking, or even maybe think about an exact step size. So rather than just taking gamma to be set to some diminishing factor, like it's on the order of 1 over k, we can try to find the best gamma along the best gamma that gives us the smallest criterion along that direction. So back to your picture, that would be like, I can't draw that 3D picture. You take the linear approximation, you look at S and X and everywhere in between, and you choose the spot in between that makes the criterion the smallest. So that would be exact step size optimization, which is often not possible for the same reason as it's not really possible with gradient. So we can instead use backtracking. And there's a bunch of other variants. There's now like probably over 5. So they're all interesting, and they all have the same properties that I've listed for you pretty much, but they kind of have increasing complexities. One interesting update is called the fully corrective Frank Wolfe, which is that at every step, okay, you look at essentially the atoms that you found in the previous step. These are the things that minimize the linear optimization oracle. This is your initial point. This is the first thing found, the second thing found, all the way up through the last thing found. And you directly optimize, you take the next step to make the criterion the smallest over the convex hull of the things you've seen. So this is like fairly expensive, and it's much harder than, let's say, just doing this. But if you could do this, which for some problems you can, because this is kind of like a simplex. In fact, this is a simplex. It's just not the probability simplex that you know. It's also called a simplex. This leads to much faster conversions, and somehow in practice, if you could do this. And then lastly, there's something called away steps, which have you moving in directions opposite to previous things you've seen, which the reason people like that is that this variant gets you linear convergence under strong convexity. So with Frank Wolfe, I've only showed you sublinear convergence under something like the gradient being Lipschitz. If you take away steps, then you get the same guarantee as projected gradient under strong convexity, linear convergence. So I'll just tell you what path following is. I won't be able to do it justice, but in case you're curious, I'll tell you what it is. Suppose you cared about solving this problem over a sequence of t's. Okay, and typically what you do is you'd optimize this at a bunch of discrete values of t. And then you do cross-validation, and then you call it a day. Path following is the idea that you maybe can try to approximate the solution path to this problem. So imagine I call x hat of t the solution at the point t. I'm going to try to actually get some suboptimality guarantee at any point t for the solution to this problem, not just at discrete points t that I lay down to begin with. So it's a much stronger version of solving the problem to epsilon suboptimality, because you're going to get a continuum of solutions that approximate the solution path. Typically, that's only possible in certain for certain structures, problem structures. With Frank Wolfe, turns out you can actually get such a guarantee just by using Frank Wolfe and tracking the duality gap. And this is the idea pictorially. Okay, suppose this is t. This is how t is progressing. I'm just going to suppose the solution. I'm just plotting it for you, like one component of the solution or something, or maybe this is just an illustration. I run Frank Wolfe to get a solution at some value, tk minus 1. Okay? I'm telling you the inductive step, basically. I say, what happens if I were to keep the solution constant? As I progress t. Don't actually change it at all. I just actually say the solution's constant for larger t. Well, what I do is I actually compute this to a duality gap of epsilon over m for some constant m. So I get a better than epsilon approximation here. I seek a duality gap that's smaller, and I increase it until the duality gap is epsilon. Okay, the duality gap, you can go back and check. As I do this, it's only going to change linearly somehow in t, based on the form of the duality gap. So it's very easy to increase this until the duality gap exceeds, until the last point in which it doesn't exceed epsilon. And then I stop, and that defines some other point tk. If I increase t past this, I would have broken my duality gap budget. And I go back and I use Frank Wolfe to recompute the solution to a different, to the same increased kind of resolution. So I use Frank Wolfe again. So Frank Wolfe, I use Frank Wolfe again here, and it gives me a duality gap. I ask for a duality gap of epsilon over m. I only stop it once I get this, and then I keep it constant again, etc., until I break the duality gap. So I think it's a fairly intuitive method, and it's only possible because of this nice duality gap that comes out, and the nice form of that duality gap, which in this parametric framework where we're increasing this parameter, t, it actually ends up being a linear function of t once you write down what it is. So pretty cool path following method. All right, I'm a little over time. Thank you guys for staying over. Happy Thanksgiving, and I will see you a week from today.